Can you hear me? Hello. Yeah, I think you can hear me. So yeah, today we are going to be doing squares and square roots, and yeah, this discussion I've kept on the side. That is what my annual exam syllabus is. So I decided to teach it to you people. So let us start. Now our chapter is squares and square roots. So in the name you have square twice, obviously. Now, what is a square in math? I'm not talking about this square, not this regular old square having all sides equal. Not this. I'm talking about a numerical square. So, you have to have a natural number, which is a number greater than 1, and which is an integer. So, it's like 1, 2, 3, 4, 5, like that. Okay. So, those kinds of numbers. You have those kinds of numbers, and you have to multiply them by themselves. So if I take 2 for an example, then 2 times 2 is 4, and 4 is the square of 2. It is also denoted by a small 2 on top of it. So 2 square is equal to 4. Then you have 3. So 3 into 3 is 9. So 3 square is 9. Then let's take another example. 4 square, 4 times 4 is 16. Then you have, let's take another number, 20 square. So here 20 times 20 is 400. So 400 is the square of 20. So this is the basic meaning of a square. So a square is a number which is a natural number multiplied by itself. It is represented by that number with a small 2 on top of it. Okay. So the next thing we have to come to in this discussion is the units digit. So if you have any number, so you know the fact, right, that if you have a number 12, 13, 144, 139, 169, anything, all of these are there, right? So the square of, if you multiply it by any number, so like if I take any number at all, like let's take 17. Now if I multiply this by 2, the last digit should be 7 times 2, 14, which ends with 4. If you do the multiplication out, you get 34, which indeed ends in a 4. So this is a property of multiplication, and it's a trick to eliminate options also in basic mathematics exams. So I'll show you another example. Let's take 153 times another number. Let's take a small number 3 again. Now if you multiply 3 times 3, it is 9. So this number should end in a 9. And what do you get? 459, which indeed ends in a 9. So yes, this property works for all numbers. If you want a 2 digit by 2 digit example, I will give it to you. It is a little time consuming. 12 times 12. Let's take it. 2 times 2 is 4, and the answer is 144. I wrote this ironically already. So yes, this property works for any number. Now the square of a number means that you are multiplying a number by itself. So when you square it, the unit digit has to be 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square, 8 square, 9 square, or 0 square. And what are these numbers that have to be the units digit? Let's see. 4 square, 5 square, 6 square, 7 square, 8 square, and 9 square, and not to forget 0 square. So here you have all these numbers which are digits. And now when you square a number, that has to end in the unit digit squared. So if I have 12 square, as you saw that time, it should end in 2 square, which is 4. Indeed, the answer is 144, which does end in a 4. Let's take 13. Now 3 square is 9, and what is the square of 13? 169, which ends in a 9. So this is what it's meant to be. So now if you do square all of these numbers, you have 1 square is 1, and then 2 square is 4, 3 square is 9, 4 square is 16. Let's just add the units digit, 6. Then 5 square is 25, which ends in a 5. 36 is a 6, 49 is a 9, 64 is a 4, and then 81 is a 1, and 0 is a 0. So the only digits that are at the ending of a square number are 0, 1, 4, 5, 6 or 9. If a number does not end in these numbers, it is not a square number. But does it mean that every number that ends in these numbers is a square number? No. So if I take 131 for an example, which are the other digits here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So does it mean that if a number ends in 2, 3, 7 or 8, it is never a square number? Yes. But does it mean that all numbers that end in 0, 1, 4, 5, 6 or 9 are square numbers? No. So if I take any example like 132, this is not going to be a square number because it ends in 2. And if I take a number like this, the ending number is 1 here. So let me take 111 for an example. This is not a square number. But if I take a different example like 121, this in fact is a square number. So the matter of fact here is, if a number ends in 2, 3, 7 or 8, it is never a square number. But it does not mean that if it ends in 0, 1, 4, 5, 6 or 9, it has to be a square number. You understood? Good. Let's move on. So this is the concept of units digit. Next, let's go on to patterns. So what kind of patterns? What kind of patterns are there in this chapter? Just a second. Just 1 second, please. Yeah. Let's get to the patterns. I need my book for this. I'm sorry. Yes. So you have triangular numbers. These are numbers which you can form by drawing a right angle triangle. So first you have a single dot, then you have a small triangle, then you have 1, 2, 3, 4, 5, 6, another triangle, then you have another triangle like this. Right. So these are triangles. Now in my textbook they have only given the pattern and they have not derived it. So I will derive it for you and show you how this came. So these number of dots here, there is 1 here, there is 3 here, there is 6 here, there is 10 here, I believe, 3, 5, 6, yeah, there's 10 here, so on. Now if you were to add any of these, so like 1 plus 3, 4, 4 is a square number, 3 plus 6, 9, that is also a square number, 6 and 10, 16, that's also a square number. This is 2 square, this is 3 square, this is 4 square, so on, so on, so on. Right? So how does this work? It's a nice question, right? So let us try to derive this mathematically. This interlinks with algebraic expressions and identities, which I will teach you later. So we need to see how are these formed. So first one is formed by just 1. This is formed by 2 plus 1. This is formed by 3 plus 2 plus 1. And then the next one is formed by 4 plus 3 plus 2 plus 1. And then so on, right? So wait a second. Let me think. How do I prove this? You can analyze it visually, for example. Now if you were to take the small square here, where is my laser pointer gone? So here, if you take this small one and move it up here into this place, this becomes a square. Now if I were to take this triangle and flip it over into here, then this whole thing becomes a square. And then if I take this whole thing and flip it over here, then this whole thing becomes a square. You can analyze it visually, and for the mathematical proof I need to think for a little. So how do I do this? This is a little tricky. So first of all, let's analyze the squares. So squares here, right? Squares. So here, this is 2 plus 1 plus 1 is 4. This is 2 square, which is this number square. This is order 1, this is order 2, this is order 3, this is order 4, like that, so on, so on, so on. So 2 plus 1, so we have to prove that. So let's just generalize the question. So 2 plus 1 is equal to 4, which is equal to 2 square. Then in the next one we have 3 plus 2 plus 1 plus 2 plus 1 is equal to 3 square. No, is equal to 4, right? Come on. Why am I acting this stupid? It is 9. 3 square, which is 9. Then the next one is 4 plus 3 plus 2 plus 1 plus 3 plus 2 plus 1, which is equal to 4 square is 16. So like this, we need to prove that the sum of the first n natural numbers plus the sum of the wait a second, can I do it like this? So this order I'll take it as n. Okay, now I can take this as 4 plus 3 plus 2 plus 1 plus 3 plus 2 plus 1. So this becomes 4 plus 2 times 3 plus 2 plus 1. I can do it like this. So this is n and this is 2 times summation of first n natural numbers. I can do it like this. And now, do you know the general formula for sum of first n natural numbers? I hope you do, because I am going to use it now. And what do we have to prove this equal to? N square, right? This is all n square. This is n square. This is n square, because n is 2 here, here n is 3, here n is 4. And next, now we have to prove this. It's already getting long. I can't post this on YouTube, sorry. Now I need to speed through this. Okay, so we need to prove this equal to n square. Now we have 2 times, what is the general formula? N into n plus 1 by 2, right, is equal to n square. We need to prove this. Now 2 and 2 gets 2 and 2 get cancelled, and we need to take n plus n square plus n is equal to n square. Am I wrong here? Yes, I am, because we need to take sum of first n minus 1 natural numbers, because we are not doing sum of up to order, we are doing up to order minus 1. Or actually scrap this, I'll take this in a different way, this question. Okay, so I'll interpret this 4 plus 3 plus 2 plus 1 plus 3 plus 2 plus 1 as this. So I'm going to write this one down again. 4 plus 3 plus 2 plus 1 plus 3 plus 2 plus 1. I'm going to interpret this as 4 plus 3 plus 2 plus 1 plus 4 plus 3 plus 2 plus 1 minus 4, because I added another 4 right in the second sum. So I can write 2 times 4 plus 3 plus 2 plus 1 minus 4. You understood why? I hope so. Next, if you didn't understand, I'm going to explain again. You have that sum here and again that sum here. Now if you sum these sums, if you add these sums together, you will get 4 extra, because there's a second 4 extra in the second part of it, right? So to remove that 4, we need to subtract 4. So this can be expressed as 2 times sum of the first n natural numbers minus the nth natural number. So if I speed through this again, I hope you'll understand. 2 into n plus 1 by 2 divided, minus n. Now this n and this 2 and 2 get cancelled, then you get n square plus n minus n, and this n and cancel, you get this desired result. So we need to prove this equal to n square, right? N square, n square, n square, n square. So we have arrived at a conclusion. Therefore, yes, this is a mathematical proof for the triangular numbers. Okay, if you want, you can screenshot it right now. Done. Moving on. I am going to delete this now. Delete and delete. Okay, next, moving on. So reverse of this, number of numbers between two consecutive square numbers. So if I have 4 square and 3 square, how many numbers are in between this? We need to check first. So we have 16 and 9. How many numbers are in there in between this? 10, 11, 12, 13, 14 and 15. How many numbers are in between it? There are 6. So is this 16 minus 9? Wait, yeah, it is 16 minus 9 minus 1. There's 1 less than 16 minus 9. I hope so. Wait a second. I forgot its fraction. I don't do it much anymore. 9, 10. Yeah, it's 6. Just a fucking minute. 4 and 6. Yeah, it's 7. So it's 1 less than the difference. Sorry, I'm bad at mental math. So it's 1 less than the difference. So this number of numbers is 1 less than the difference. So I'm going to take this number as n square. Okay, let me show you what's going on here. Between 16 and 9 there are 6 numbers, which is equal to 16 minus 9 minus 1. And the other way you can do it is, let's take another example. 3 square minus 2 square. Now this is 9 and 4. 9, 4, 5, 6, 7, 8. Now how many is this? 4, which is 9 minus 4 minus 1 is equal to 4, right? So the number of numbers in between two consecutive square numbers is the difference of the squares minus 1. And what can be expressed as difference of squares? A square minus b square is equal to a plus b into a minus b. Again, algebraic expressions and identities, not adversaries. Sorry. Okay, so let's take a mathematical proof. So okay, so that this is equal to a plus 1. Sorry, no, this is equal to this is equal to, according to me, a plus b into a minus b minus 1. So if you want the proof, I am going to show you, and really fast. Okay, so we started off with a square minus b square minus 1, right? Now a square minus b square can be expressed as a plus b times a minus b. If you want to expand this, I will show you how to do it right now. So a times a square, b times a plus b, ba. So I'll write that as ab. Then minus of ab, right? Because a into minus b is minus ab. Then next one is plus b square. Sorry, is it plus b? No, it's minus b square minus 1. Now plus ab and minus ab will get cancelled, which is a square plus b square plus 1 minus 1. So that's all. So this identity you need to keep in mind. Now I'm going to start erasing the proof. Goodbye. So goodbye to the proof, and no, I do not want you people back. Oops, I got them back from the shadowland. Get out. Sorry, get out of here. Okay. Next, what did I do? Yeah, I just completed difference between two consecutive square numbers. Yeah. So the other thing is that I need to drink water. Just a second, please. Um, Next, moving on. So we have sum of first and odd numbers: 1 plus 3 plus 5 plus 7 plus ... We need to prove this. So I'm going to show you something here. Okay, let us take 1. Can we express it as 1? Yes. Let's take next square number 4. Can we express it as 3 plus 2? No, 3 plus 1? Yes. Can next square number is 9. Can we express it as 5 plus 3 plus 1? We can. Indeed. The next one number is 16. Keep going. What's the next odd number? 7 plus 5 plus 3 plus 1. This is amazing, isn't it? So, how can we prove this? Now, you can see that these two parts are identical. This part and this part. So, can't I replace this with the previous number? I can. I can indeed replace this with the previous number. So, this happens all the time. So, if I were to box in the next part, this 1 comes here. Then, this one whole thing comes to here. Like this. So, if I were to take this number as n, okay, and the previous number here as n minus 1, so I know this number is n square and this one is n minus 1 square, right? Because it's the previous number square. And this is the nth odd number, right? And what are the odd numbers? 1, 3, 5, 7, so on. Can I express this as 1 into 0 times 2? Sorry, 1 plus 0 times 2. Can I express this as 1 plus 1 times 2? Yes. This as 1 plus 2 times 2? Yes. This as 1 plus 3 times 2? Yes. So the nth odd number, first odd number is 0. Second odd number is having 1. Next one is 2. Next one is 3. So the nth odd number is equal to n minus 1 times 2 plus 1. Or I can express it as, in the other way to do this is, get rid of this, I can express this as 2 times 1 minus 1. I can express this as 2 times 2 minus 1. Then guess. Obviously it's 2 times 3 minus 1, 2 times 4 minus 1, so on, so on, so on. So the nth odd number, we can keep it equal to, nth odd number is equal to 2 times n minus 1, right? And which odd number is this? This is the fourth odd number, and this n is equal to 4 here, right? So this is the nth odd number, which is 2n minus 1, and this is the n minus 1th odd number, which is 2 into n minus 1 minus 1. Do you agree with me till here? I hope so. So all we need to prove is that this number here is equal to this number, which is this, because if you put this, yeah, let me explain again. We have to prove that this number is equal to nth odd number, sorry, why am I struggling to explain? So this is the nth number squared, right? So this is the square of the nth number, and this is equal to the nth odd number plus the n minus 1th square number. This is also, wait a second, did I do something wrong here? Of course I did. Yeah, I'm bored. Anyway, this is wrong, absolutely wrong. I am so sorry if this confused any few people. This is n minus 1 square. I am so sorry. So yeah, we need to prove it that this is equal to this is, yeah, not less. We need to prove that this is equal to this plus this, which is n square is equal to 2n minus 1 plus n minus 1 square. So that's the only thing we need to prove here. N square is equal to 2n minus 1 plus n minus 1 whole square. So now I'm going to blaze through the calculation. So n square is equal to 2n minus 1 plus n square plus 1 minus 2n, because this is general form of n minus 1 whole square. Sorry, a minus b whole square is equal to a square plus b square minus 2ab. Now plus 2n minus 2n cancels. Then what is remaining here? 1 and minus 1 cancels. N square is equal to n square, right? Because then this 0 is equal to 0, obviously. So then this is true. So we have proved the identity. So you can express any odd number, any square number as the sum of odd numbers, right? The other way you can talk about this is in this way. So it's called square root by subtracting odd numbers. Okay, now I'm going to take this number, just a second, someone messaged here, 1 second. I think this is our Kannada essay writing, which is not essay writing, Varati, which is there for exam. Okay, moving on with our math lesson. Okay, so I can take 25 and go on subtracting odd numbers from it. Will we reach 0? Let's tell. Is 25 a square number? Yes, note it. Square number, right? It's a square number. So let's go on with this. 25 minus 1, 24. Then next square number is 3. Sorry, odd number. Next odd number is 3. Subtract 3 from it. What's there? 21. Then next thing is we have 21 minus 5. 21, 20, 19, 18, 17, 16. I am slow. Next we have 16 here. Then number 4. Subtract next odd number 7. 16 minus 7 is equal to 9. Next odd number is 9. 9 minus 9 is 0. So you can see we eventually reach 0 for this square number. Let's take a different square number. 16 square number, right? Let's go on with the same process. I'm not going to write the index number, what do we call that now. 16 minus 1 is 15. 15 minus 1, I'll write it like this. 16 minus 1 is 15. 15 minus 1 is 2. 15 minus 3 is 12. 12 minus 5, which is next odd number, 12. 11, 10, 9, 8, 7. 7. 7 minus next odd number, 0. So we end up with 0 in the end, right? So if you take any square number and continuously subtract odd numbers from it, you must reach 0. The other way around is also true. So if you have a non-square number and keep subtracting odd numbers from it, you will not reach 0. So this is called square root by subtraction. So the reason I wrote these numbers here is because how many steps did we take here? We took 5 steps. 5 steps. What is 5 square? 5 square is 25. So if 5 square is 25, then what square is 25 is the question that root 25 will ask. Square root of 25 is 5 because 5 square is 25. The square root of 16 is 4 because the square of 4 is 16. So it's like a reverse question. If n square is x, then what is square root of x? N. That's how you should do it. Okay. So it's a reverse question. You understood it? So this was one more part of our lecture. Sorry, I won't call this a lecture. It's more like a discussion. Like we found interesting patterns and all that, no? So it's more like a discussion between a couple of nerds. Yeah, moving on. Some of the first 10 odd numbers. Did we do this yet? No, we didn't. Should have added it into that same part now? Yeah. So let's sum first 10 odd numbers. 1 plus 3, 1 plus 3 plus 5, 1 plus 3 plus 7. Can do it like this. 1 3 plus 5 plus 7. This, what is the sum? 1, next one 4, next one 9, next one 16, next one dot, dot, dot. Here also dot, dot. So if you have n odd numbers and you sum them, you will get the nth square number. This is the same as that property, no, which I told it before. So the sum of the first n odd numbers, sum of first n odd numbers is n square. Got it? Now how can we prove this? This is a little harder indeed. Okay, so the first odd number is 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus 2 times 4 minus 1 plus so on 2 times n minus 1. First n odd numbers is equal to n square. We need to prove this, right? Then you have how many minus 1s here? You have n minus 1s, right? So let's just write down a minus n at the end. Why is my dad honking? So sorry, there is a bit of mistake here. So no one is talking in my family. Wait a second, I'll be back.